The pings had basically three pieces of information. The first was the time that they occurred. The second was something called the burst timing offset, and that is, and the third one was this burst frequency offset. Problem of trying to work out where the plane could have gone was really a problem about triangles on a sphere. The last radar contact was roughly here. And then the plane, the first two pings were on this blue arc and that blue arc. And then they came back across these 5 other arcs. Distance from the satellite to the center of the Earth was actually 6.5 times the radius of the Earth. It shows the trajectory of the flight path of the plane. It started in Kuala Lumpur. You follow the numbers, 1, 2, 3. Then there was a very sharp turn here, another sharp turn, it came out here, and then it got out of radar contact. The blue curve shows actual real data, BFO data. The green guy is the Doppler shift, or the BFO, of the track going south, and the red one is the one going north. And you see the agreement is much, much better with the southerly route than with the northerly route.
Good morning, good afternoon, and good evening to our audience from around the globe. This is your host, Sid, and it is wonderful to have you back with us for another episode of the Sit Down with Sid podcast, where we bring people together one conversation at a time. A quick note before we begin. MH370 remains a complex mystery with many conflicting theories. The views expressed by our guests are their own. Our goal is to provide a platform for various perspectives as we continue to piece together this permanent digital archive in our MH370s series. Joining us today is Dr. John Zweck, a distinguished mathematician and researcher specializing in applied mathematics, data science, and the rigorous analysis of the satellite telemetry data. Dr. Zweck's independent academic work on the Inmarsat satellite handshakes brings a critical mathematical lens to understanding the flight path and terminal trajectory surrounding the disappearance of Malaysia Airlines Flight MH370. Dr. Zweck, you have spent your career mastering complex applied mathematics and translating noisy, high-stakes data into clear geometric insights. You bring a unique analytical level perspective to this mystery that very few people can offer. It is such a pleasure for us to have you here on the show, and thank you so much for taking the time.
Thank you. It's good to be here.
Thank you. Okay, Dr. Zweck, so for our audience meeting you for the first time, could you share a little bit more about your background and how you personally got involved in the disappearance of MH370?
Yeah, so I'm an applied mathematician. At the time that, back in 2014, I was at University of Texas at Dallas, and I was teaching a Calculus 3 class. And so that's sort of understanding how functions and things change in 3 dimensions. And we were about to do the lecture on spherical coordinates. So that means longitude and latitude coordinates, which most people, who've seen a map have some understanding of. And at that was exactly the same day, around March the 8th, 2014, that we saw in the press that this plane had disappeared. And so I come from Australia, and so I was immediately interested from that point of view because it's in my neck of the woods. And I sort of saw a picture in the Washington Post online, and it had these picture of these, like this arc in the on a map, and they said the plane disappeared somewhere along this arc, and there was an arc that went into the northern hemisphere into Central Asia, and an arc that went into the southern hemisphere into the southern Indian Ocean. And I thought, my God, how did they know that? And then the next day, they had not just one arc, but they had like 5 or 6 arcs. And I thought, well, that's even more interesting. And they had some more detail about it. So that sort of like got me interested, because I sort of immediately knew that I could use some idea about geometry on spheres. So in high school, you learn about geometry in the plane and your triangle geometry and stuff like that. You know what a right triangle is, and you know Pythagoras' theorem that tells you what the length of the hypotenuse is on a right triangle. And I immediately sort of saw that the problem of trying to work out where the plane could have gone was really a problem about triangles on a sphere. And so this is very simplistic, right? I didn't know anything about the way airplanes worked. You know, I didn't know anything about autopilot or headings or any of that stuff. I didn't know any of that. So I just thought about it from a very simplistic, high level point of view. And, you know, over the next week, there was more and more information that was released by the Australian Transportation Safety Bureau. And so I sort of started to follow that information, and I thought, well, maybe, and they didn't really explain very much. Okay. So they didn't explain very much about how they were getting their answers, and they seemed like they were really busy. And I sort of began to understand that you could explain basically what had happened in very, very simple language. So I actually got an interview with an NBC news reporter, and there was it wasn't a video thing, it was a written NBC science reporter. It was a written article on their website where I talked about how you could understand what was happening in terms of like moving a string around the surface of a basketball. And so I sort of thought, well, let me try to sort of, if there are opportunities that arise, I will try to translate what these people are doing, trying to find the plane, into sort of simpler terms. And then shortly after that, they released this this information that said, we've used this Doppler shift data to be able to determined that the plane had to go south rather than going north. And I thought, wow, that's like really, really cool. So I have this background in applied mathematics, but I started out doing more pure mathematics that wasn't connected to the rest of the world. And then since the last 30 years, I've been doing applied mathematics, where I like try to work with engineers solving engineering problems using math. And so I'm very comfortable starting out like learning about a completely new field and like just running with it. And so that's what I sort of decided to do here. It sort of absorbed me from that March the 9th until October 17th that year, when I sort of had an article that I submitted to an applied math journal. And then I sort of like let it go after that. So that was my initial interest in this. And initially I learned a lot from, there were sort of two places where I got information. The first place was from the things that were released officially in the newspaper. And then that mostly came from the Australian Transportation Safety Bureau or reports. And then I started to get hold of their preliminary reports and read them directly. And then there was this, basically back in 2014, we still had blogs. And so there was this very active blog that had a lot of people who seemed to have a lot of knowledge about what really goes on with satellite communications, what really goes on with aircraft. And so, you know, there were like reams and reams of posts in this, and they put some data up there. And, you know, I read through this stuff, and some of it was I didn't find helpful, and some of it I did find helpful. Some of it was really helpful. So that's where I first, for example, understood what on earth was going on with this satellite and how it was moving around. And that's also how I first understood what on earth this burst frequency offset was. It was hard to get. And so I started to work out equations and to do that described what was going on and trying to solve those equations on a computer using mathematical software. And the part of the problem is that I didn't have the best data to begin with. So, because they hadn't released it. So I sort of made up my own data of a fictitious flight between Colombo and Perth and tried to see if this method would work on that and use that as a way to sort of like help people understand what was going on. So that's sort of how it all began. So, yeah.
Wow, thank you so much for giving us such a detailed background. And here you are, all the way from Australia, now residing in the United States. Okay, so now for our audience who pretty much knows like the basic story, can you explain how the automated hourly handshakes or pings between the MH370 and the Inmarsat satellite functioned after the radar coverage was lost?
Yeah, so let me just I have some slides here from a talk that I gave a long time ago. Let me just put these up here, and I just pulled out the slides that were, I thought, most important. So here, by the way, is a picture that I found on the web. It's got the Malaysian government stamp on it that shows the region that people thought this plane went down on, somewhere near there. So and so let's see. So how do I want to talk about this? So basically, so this picture might be helpful. So there was a satellite that, can you see my cursor here?
Yes.
There was a satellite way out, a long way from the Earth. And the blue thing here is meant to be the Earth. And the distance from the satellite to the center of the Earth was actually 6.5 times the radius of the Earth. So this is not realistic, this thing. This satellite should be way out further, a lot further out. So the satellite is a very, very long way away from the airplane. So, the radius of the Earth is about 3,500 kilometers, roughly. And the aircraft was at an altitude of about 10 kilometers. So it's basically, when you look at it at that scale, it's basically on the surface of the Earth. It's a very small difference. And so what the satellite was doing is, for some reason, there was this automated check-in system where the satellite checked in automatically with the aircraft every so often. And after the last radar contact between the plane and the with the plane, the only information we have about where MH370 was due to this these pings, these communications. And they happened roughly every hour for 6 hours. And the pings had basically 3 pieces of information. The first was the time that they occurred. The second was something called the burst timing offset. And that is, and the third one was this burst frequency offset. So let me start with the burst timing offset. So basically, you can think of the satellite and aircraft communicating via some form of light. It's part of the electromagnetic spectrum. And light travels at a constant speed. And so if you know how long it takes for a signal to go from the satellite to the aircraft and come back again, then you could use that information to work out what the distance between the satellite and the aircraft is. And so when you do that, you know that there's a sphere. It's actually a sphere in space that comes all the way around here, which is the aircraft could be somewhere on that sphere. But we also know that the aircraft had to be 10 kilometers above the Earth, roughly. So now you take 2 spheres, this is the geometry problem, and you intersect them. It's got to be on the sphere, and it's got to be on this imaginary thing that's so far away from the satellite. So because they know the time that the signal took, they know the distance. And so the intersection of those 2 spheres is a circle. And it's this circle schematically shown here. Right? So they knew that the plane had to be on this circle somewhere. And so they had these 6 circles and so on. So here they are. This is a sort of zoom in, and they go, all the way around the world, but there's no point in going all the way around, because if you go too far, then the plane would have had to travel so far it would have run out of fuel. So that's why in the first slide that I showed, they just sort of show this extent, and that's sort of indicating like how it couldn't have gone further than this because it would have run out of fuel. All right, so the last radar contact was roughly here. And then the first 2 pings were on this blue arc and that blue arc. And then they came back across these 5 other arcs. Okay. So that's that information. And then, by the way, here, this little cross here is showing where the satellite was. If you look at the shadow of the satellite on the Earth, that's where it was. So it was sort of like, that's India there, and this is basically the Gulf of Arabia up here, and Africa is over on the left. Okay, so that's the burst timing offset, and that gave this information about these where the plane was. So we have what I call partial position information. A little bit about where the plane was at some times. So now, the good thing about that data, which I learned only later, is that data is highly accurate. It's very accurate. All right. The error in that data is very small. And I think even in the most sophisticated modeling that I'll talk about later, that data they didn't even discuss. The burst frequency offset, that's quite different. So that comes about because of the following idea. Let me see if I can find sorry for going back and forth here.
No problem, please. This is very interesting. Thank you for sharing all of this with us.
All right. So it's basically based on what's called the Doppler effect. And if you've ever heard an ambulance come at you along the road with its siren blaring, the pitch of the sound coming out of the ambulance changes as the ambulance is coming towards you or going away from you. And the same thing happens. That's a fundamental phenomenon about the way any wave motion occurs. And light is a wave motion. And so when the aircraft was moving towards the satellite, the light that it was receiving will be more blue or higher frequency than the light that was sent. So that's a shift. It shifts towards the blue. And if the aircraft is moving away, it shifts towards the red. And so there's some physics that you can sort of work out an equation, and this is about the only equation I'll show in the whole presentation down here. Delta F here is this frequency shift, and it's a relative frequency shift. How much is it shifting relative to the actual frequency or color of the light that is being propagated? And then this thing over here, let me just turn it into plain English. So you're trying to ask the frequency shift depends upon how fast the satellite and the aircraft are moving towards each other or moving away from each other along a straight line joining the two of them. Okay, so in reality, the satellite is moving around like this. In reality, the aircraft is moving like that. They're both moving, but you don't look at and so there's some relative velocity between them, right? The velocity between them could be like in that direction, but you're only looking at the part that's along the component of it that's immediately between the two, right? You sort of care about motion that's parallel to the line of sight, not perpendicular to it, not at 90 degrees to it. So that means that Doppler shift information gives us partial velocity information, gives us some information about the speed and the direction of the aircraft relative to the satellite. Okay. Now, they didn't measure this directly. They measured it through something called the burst frequency offset. And, okay, so I'm showing you a second equation, all right? So this burst frequency offset is something about the way these satellite communication systems are designed, all right? And the term that I was talking about, the Doppler shift, is here. And there are a bunch of other terms in this equation, and I only want to talk about one of them, which is this bias here. And the reason that I'm talking about that is that there is significant uncertainty in how much that bias frequency is. The nominal value was 150 hertz, plus or minus 5 hertz. And plus or minus 5 hertz might not sound like a large error compared to that 150 value. 5 out of 150 is not very much. But it turns out, as we'll see later, to be really, really important. And so that sort of unknown quantity was one of the reasons why it's much harder to understand why the where the aeroplane actually went with a great degree of certainty. That's one of the reasons for that. So what the satellite engineers did is they got the burst frequency offset measurements, and then they extracted the Doppler shift out of that because they knew something about all these other terms, although there was uncertainty in this term. And then they were able to sort of like thereby get some idea about what this velocity of the two guys, the plane and the aircraft, were relative to each other on that line of sight. Okay, so is that good?
This is great.
All right. Let me go back here. So what next?
Yeah. So you can walk us through these presentations if you want, one at a time, if you would prefer that format. So our audience.
No, I like your. You had some questions that you sent me. I really like the order of those. So let's go with that. Yeah.
Okay, that's fine. Do you want to leave the shared screen on, or do you want to take?
If it's okay, I'll leave it on because I'm gonna keep coming back to it.
Let's do this. Okay. Now, since you talked about the BFO and you also mentioned the BTO, now can you tell us how do these work together to turn a raw frequency variation into a usable geometric data? Is that the slide that you were showing with the formulas? Did you already cover that part?
Okay, let me not tell you how to do that yet, because that comes later on in realistic questions. Let me use it to turn it into a math problem. Okay, I'll state the math problem. Okay, so the math problem is the following. I know something about where the aircraft was at certain times, and I know something about the speed and the direction of the aircraft at those same times. And in fact, and so then the question is, from those pieces of information, can I work out where the aircraft might have gone? Right. And so I think that's a geometry problem. The way I think about it, that's a geometry problem. So I just sort of talked to you about how we're turning that raw frequency BFO data into Doppler shift, which gives this partial velocity information, this partial position information, right? So if you knew, so that's the goal, right? And there are potentially multiple answers to this question. This is what's called an inverse problem in mathematics, where inverse problems have this character that there are potentially many solutions that are all equally good, right? And in this context, it's made more difficult because the data is not perfect. I already talked about the issue with that bias in the BFO data. And so the data is not perfect, so you're not going to be able to get a perfect solution to this problem. So then that means that you're going to have to incorporate that uncertainty somehow, and there are different ways to do that, which we'll talk about.
Got it. And do you think the data is not perfect because of the plus minus 5 hertz that you mentioned in the formula?
That's one of the major places. There's another piece of information that is really, really crucial, and that's the following. And maybe I'll just show this picture here. This is from the Washington Post on March the 17th. And it shows the trajectory of the flight path of the plane. It started in Kuala Lumpur. You follow the numbers, 1, 2, 3. Then there was a very sharp turn here, another sharp turn, it came out here, and then it got out of radar contact. And so obviously things were going on with these sharp turns, and this whole thing is a great tragedy, and I really feel for the people who were on the plane at the time, and I really feel for their families. This picture is the only real information that I have that something very bad was going on somehow, right? Anyway, so now even after this lost radar contact, there was one of these pings shortly thereafter, but the satellite engineers and the people that who were investigating this whole thing with the ATSB, they discounted that first ping because it didn't seem very reliable. And so then the second ping happened 90 minutes after the last radar contact. So the last radar contact, we know exactly where the plane was, and we know pretty much what its speed was, its direction was. And then there's a 90-minute period where the plane did we don't know what. And so before the next ping, all right? And so as I'll show you later on, if you want to solve this problem and you want to work out where the plane was, you really have to know, and you just want to use this ping data, you have to know where the plane was at the beginning of the first ping, and you have to feel confident about that. And the problem is we don't have confidence in that. And that lack of confidence is a greater source of error than this bias error in the BFO. And that lack, and the ATSB teams, what they did is there's all this situation where they changed the search area multiple times between March and June. And they did that in large part because of the fact that they sort of got different clues from various sources as to where the plane might have started on that first arc that's reliable.
Interesting. Okay. So I'm going to go in the same sequence of the questions that I sent you, and you can let me know which one you want to go for first. So let's talk about the Inmarsat satellite was not completely stationary. It had a slight orbital motion of its own, as you showed in the diagram initially. How did the mathematicians isolate the satellite's movement from the movement of the aircraft?
Okay, well, the mathematicians didn't do that. That was satellite engineers.
Okay, so let's change it to satellite engineers.
So, in fact, it might not have been even these satellite engineers. There's a database which satellite engineers or the satellite communications community keeps, where they show the location of every satellite that's known up in the sky as a function of time all the time. And I guess they want to keep track of where they are, right? See whether some fall out of the sky because they come to the end of their useful life or whatever, or you want to point your satellite receiver in the right direction. So this is a publicly available database. And some people in this they would call the alternative work group, I think. I might have the name wrong, but this long blog thing, they posted the actual satellite data. So you could download a file which had a whole lot of numbers in it, which said, at these times, here's where the satellite was. Okay. So I'll show you the picture of it. So this is a picture of that. The blue is the picture that comes from the data. And I sort of it's really like a lot of little dots, but I joined them in to make a curve. And you notice that what's going on here. This is the latitude. So that's like north-south direction. The vertical axis is like north-south, and the horizontal axis is like east-west. And so we're going from -1.5 to 1.5 degrees in latitude. And so but we're only going across 0.1 of a degree in longitude. So this thing is really very, very, very thin. It's very elongated. Okay. All right. So that's called a geosynchronous orbit. So once a day, it comes back to the same position, basically, over the Earth. So this is the shadow of that motion of the satellite onto the Earth. And so it comes back once a day, and well, it doesn't come back quite exactly, right? So ideally, ideally you would like to have the satellite just sitting there in one place. That would be called geostationary, but that doesn't really happen because if the only gravity effect that there was due to the Earth, then you could work out where to put the satellite, how far to put it at. It's about 40,000 kilometers out from the Earth, so that it would be exactly geostationary. It would just stay there in the same spot. That doesn't happen. It would stay over the same spot of the Earth. Now the Earth is rotating, so the satellite is also rotating, right? And they're rotating at the same rates, so that the shadow would be exactly at the same spot. In reality, that's not what happens, because the satellite is also affected by the gravity of the moon and the sun. And so instead of this thing moving in a beautiful circular orbit around the equatorial plane, it's moving in a plane that's slightly tilted with respect to the equator, and it's moving. It's not moving exactly in a circle in that plane. It's got a little wiggle in that circle, and the wiggle is about 1/2,000th of the radius of the circle. So it's a very tiny wiggle, right? But because of that tiny wiggle, that's what causes the shadow of that satellite motion on the surface of the Earth to be going around in a curve like this, right? So I came to understand all this because I developed a mathematical model to predict where the satellite that explained the satellite motion from a mathematician's point of view, and then that's the red curve, right? And they don't look exactly on top of each other, but the shadows are within about 6 kilometers. The position error was about 6 kilometers on the surface of the Earth, and the velocity was with less than 0.5 kilometer per hour, right? So that's pretty accurate. So I felt like I sort of understood what was going on with the satellite. So, okay, so yeah, and so, all right. So now, what's the point? So you asked how you isolate the satellite motion from the motion of the aircraft, and the short answer is it was in the data on the web.
Wow. And would you walk us through? So the reason I'm asking this question is, a lot of people have said, why not the northern part of the Indian Ocean? Why the southern Indian Ocean? So would you take a moment to walk us through how the frequency and timing measurements ultimately pointed investigators towards the southern arc in the Indian Ocean rather than a northern path? And do you think the Doppler shift was that critical element that actually ruled out the northern arc for them?
Yeah, so this is the thing that I am surest about in this whole story. This is uncontrovertible, in my opinion, from a mathematical point of view, from all the data, and all the modeling shows that this is really what happened. So this is really sure. And it's backed up by the fact that there was debris that was identified off of Reunion Island in the southern Atlantic Ocean near Africa. So the basic idea is the following. So, all right. So let me sort of go back here. All right. So actually, before I do that, okay. So, all right. Let me show you this. Okay. So now I made a fictitious flight that went from Colombo in the south of in Sri Lanka to Perth. And I had that flight, and then I sort of like recorded several times where the blue circles are, where I knew where the plane was. Okay. And then let me just sort of go back. Let me go a bit out of order here so I can show you the sort of story here. So here's the satellite. There's Colombo. And Perth is down here. All right. And I had some ping circles, right? So I knew that the plane crossed these circles at this times. And so I had to work, and I knew that these, and I also knew the distance that the plane went to go from this circle to that circle, because I knew the times that it took, right? That's the burst time offset. So I knew that this is the distance that it had to go from here to that distance to get to the first circle, and from here to there to get from the first circle to the second circle. And now I've inadvertently started this movie, and you can sort of see, you move that green guy around, and you wait and you see when they line up, when there, right? You see the, let's just go back a little. Does it want to stop? All right. Like right there, because I had perfect data, right? Right there, they line up, right? So I know that if I had the plane going along this path, it would hit the red circle at the right time. It would hit the next red circle at the right time. It hit the next red circle at the right time. So that's a potential path that could have happened. And all the other ones where you don't hit the circle at the right time don't work, right? Now, in order to do that, I had to make an assumption about how fast the plane was going. So in this one, I had the plane going at, at 800 kilometers an hour, 450 knots. Whoops. Oh, I'm sorry. Okay. All right. So now I want you to watch this, because there are actually two places there. And there's another place later on where they'll all line up. We have to let the movie run almost all the way around. So it's definitely not lining up because this guy is way off here. All right, we come around again, and you'll see it happen a second time. There, right? Okay. So if you change the velocity of the aircraft, the speed of the aircraft in this simulation, then those places where they line up will change. All right. But there are two of them. That's the point. Right. So mathematically, you can prove there will always be two. All right. Now, the issue is that, so here's this Colombo thing again, right? You know, this fictitious flight. And the question is, with this fictitious flight go to Perth, or did it go straight up there? Right. And the point is that with the satellite was perfectly stationary, you could not tell the difference. It would be impossible to tell the difference between the two. But the fact that the satellite was moving itself at the same time, so in 24 hours, the satellite goes once around that funny curve. And this flight took over about 6 hours. So it's going about a quarter way around that curve. And it goes a quarter way around that curve. As it's going, its velocity is changing. And the velocity of the plane is also changing. So because of the fact that those changes were occurring, the Doppler shift would be different down here than it would be up here. Because down here, the satellite was going in one direction, and up here, the satellite was going in another direction. And as a consequence, that's really the reason why the Doppler shifts would be different for this path compared to that path. Okay, does that make sense?
Yes, this is really fascinating, actually. Thank you so much for educating us on this.
Right, and so now let me try to find the slide which has the actual data. Oh, damn. There, okay. So this was released by one of the government research agencies on March the 25th, 2 weeks afterwards, after the accident occurred. So the blue curve shows actual real data, BFO data. So this is like Doppler shift data in disguise. And then they took the tracks that they sort of like, they had by this point, they basically solved the problem that I showed in the video a minute ago. And they had a track going south and they had a track going north. And the blue, the green guy is the Doppler shift, or the BFO of the track going south. And the red one is the one going north. And you see the agreement is much, much better with the southerly route than with the northerly route. And notice how different these are. This is a 100 hertz gap, right? And I said that there was a 5 hertz error in this thing, right? So that error is gonna be tiny compared to that gap. So this is very, very strong evidence that the plane went south. And I did the same simulation for myself, and I got the same result. It's very clear. And I derived equations, and you can see from the equations that it should happen too.
Wow, this is excellent. Thank you once again. I want to talk about your SIAM review paper. In that paper, you introduced 3 progressive mathematical models to reconstruct the flight path. Could you walk us through how those models build on one another in complexity?
Sure. So SIAM is the Society for Industrial Applied Mathematics, and it has a journal article that goes out to all the members, and I got my article published there. And a lot of the figures that I'm showing you there are in the article. So let me see. Okay, so I had 3. What happened was that our knowledge of what the data was changed over the course of a month. All right. And so, I just want to point something out here. This was a great tragedy, but it was also, and you alluded to this earlier on, it was also an opportunity for the public to see a very highly skilled group of engineers from very many different backgrounds working for government organizations and major companies like Inmarsat and Boeing, and the public at large who had expertise in this area, grappling with a highly complex problem in real time. Right? And I thought it was a wonderful sort of way to view how science progresses. And engineering is sort of science, right? So this is really trying to discover what was happening, and people changed their minds they changed them. Their minds were changed for them by the data, right? And so we rigorously follow the data and we try and interpret it. And so as a consequence, the mathematical models that people used to try to tackle these problems changed in several ways. And I was working sort of basically by myself, accessing their data, and I changed my approach too in similar ways. And so I had 3 mathematical models that I used, and the first and the third of them actually have some similarities with the 2 major models that the official government groups had, but mine were much simplified in some respects. So first of all, let me just say a little bit about what do I mean by a mathematical model, okay? So we have data, all right? Those ping arcs and the Doppler shifts at certain times. That's all we have to go on. And the question is, okay, if we want to ask where the plane went, we have to make some assumptions about what the motion of the plane was. And so you make some assumptions, and you try and make the assumptions to be as simple as possible, but also as sort of like, close to realistic as possible. So there's this trade-off there, right? And so you want a simple model that captures the real essence of what was going on with the motion And then using that model, you use the model to derive equations, mathematical equations, and then you try to solve the equations to predict what would happen, what actually happened. So that's the process that we go through. All right, and that process is ubiquitous in engineering, in all across engineering. So what I did, my first model, I just assumed that the aircraft had a constant speed over the ground and it was flying at a constant elevation. And I assumed that I knew the initial position and speed of the aircraft, but I didn't know its initial direction. And then I assumed that between one ping arc and the next, the plane was not accelerating. It was going in a straight line, right? Well, not really a straight line, because it was traveling on the surface of a sphere. So if you're traveling on the surface of a sphere and you don't want to, you're on the sphere, so your elevation isn't changing, and you're going in a straight mountain, that means you're not turning left or right. And so that means that you're traveling on what we call a great circle. And the simple example that we all know of the great circle is an equator. Is the equator. It's the largest circle that occurs on a sphere. But there are all sorts of great circles on a sphere. You take a sphere and you intersect it with a plane, and the plane, if the plane goes through the middle of the sphere, then you always get a great circle, right? So lines of longitude from the North Pole to the South Pole, those are great circles. So there are lots of great circles on the sphere. So I assume between one ping arc and the next, we had great circle motion. All right, so I knew the direction the plane was going. I knew its speed. And then I assumed that the satellite was geostationary because I didn't know about initially, I didn't know about this motion of the satellite. All right, and I didn't use the Doppler shift data because nobody knew about it at that point. So when I did that, that's how I made this video that I showed you a while back, right? All right, and then when I did that, I got these results, which are very similar to results that came out of the ATSB. So, and you sort of see that you get different paths depending upon the different speeds that the plane was going at. So a knot is a nautical mile, and 450 knots is about 830 kilometers an hour, right? I think in kilometers an hour. So if the plane was going faster, it could go further, and it followed that track. If it was if it was going slower, it could follow the blue track. And notice that's about 125 knot difference, 125 miles an hour roughly difference in speed, and it goes from one end of Australia to the other. That's like going from Seattle to all the way down to Baja California. That is a long way, right? A very, very long way, right? And not only that, it's going way out that in the Indian Ocean, and the distance is even further because it's sort of got a component in that direction. So that's a big difference. And then there was also around the time this came out, that's where the last radar contact was. And I said there was 90 minutes between the last radar contact and the first ping. So these guys occur on what we call the first reliable ping arc. And the question is, you've got to pick a place there, right? So initially, people thought it was about here that it probably was at. That was a guess. And then later on, they had some more data that suggested it was actually out here, a little further out. So I chose a different place. And then you get the intermediate route. Okay. So that's the first model. And here we're assuming that the plane has constant speed. And it's traveling along these great circles. The question of, those assumptions might not be valid, right? We don't really know, okay? Second model, and so like that's the ATSB stuff, came out around the same time. And, they moved initially they were looking down here, and then they sort of said, well, we think the plane went a little further out, and so then to get a match, you had to go here, all right? And so that's sort of like the distance between my two guys, all right, very roughly. And so they moved the search location up here for a while. And then, like, a lot later, it got moved back down here. So that's sort of, there was, and that's all, a lot of that's due to where was the plane at 1941 GMT, right?
And the speed as well, right? As you showed in your model.
Right, that's right. And the speed is also, you have to choose different speeds to make that work, right? Exactly. But that's right. Yeah. Okay. So second model was, I don't think I even want to talk about this model because I don't really use it. So I'm going to skip to the third one. Okay. All right. So in this model and the second model have a lot in common. This model is a bit more realistic. So in this model, instead of looking at assuming that the path of the plane was along a great circle, I assumed that it could have gone along what we call a small circle. So between two ping arcs. So that may not be very realistic, all right? But basically, the idea is that the plane, due to wind or maybe the slight tilt of the wings or something, maybe the plane could have like turned a little bit. And the amount that and I was assuming that between two ping arcs, it was turning at a constant rate, right? So the fact that it would be doing that over the course of an hour is not very probable, but I didn't have anything better to go on. And I wanted to allow for a little bit richer set of possibilities. So I had these small circles. So a circle of latitude, like the Arctic Circle, is an example of a small circle, but there are small circles all over the sphere. And so I had that. And then I also used the BFO data. So I incorporated the Doppler shift. And I incorporated the possible errors in the BFO data, all right, in a sort of ad hoc way. And so what I did was, what I did there was I basically, let me just see if what I did there was I came up with an equation. I sort of insisted, in my model, insisted the following. It insisted that at each ping time, the aircraft crossed the appropriate ping arc. And I insisted that it had the correct Doppler shift on that arc. And then I asked, how should it go to get, what small circle should it travel on to get to the next ping arc? And so that when it got there to the next ping arc, it had the correct Doppler shift there. So those were the constraints that I built into my model. And when I did that, when you do that, you see that, and so I couldn't solve those. There were equations that I wrote down. I couldn't solve them exactly. I had to solve them in what we call a least squares sense. So I tried to sort of make the some error small. And it's, so that was my approach. And when I did that, I got curves that I got. This is an example of a curve that I got, all right, through that. And so what I did is I sort of said, so I could get, I sort of said, well, how am I going to, I could get lots, so there were, okay, so there were, remember there was this uncertainty, right? So the plane could have started anywhere along here on that arc there, because we'd lost contact for 90 minutes. So that was sort of a guess as to where it started. So I started at lots of places along here. And then I gave it lots of possible, these bias terms in that BFO thing. That'll change what the effective Doppler shift was. And then I sort of said, okay, for each of these, I'm going to make a flight path and I'll start on lots of the appropriate places and I'll get somewhere down here. And then I'll ask, how good is the answer that I got? So over here, you see all these little blue circles. Each one of them represents a different simulation that I ran that looks like there are about several hundred of them. And the bottom of this curve here is saying, I'm going to, I want to sort of make I tried to find the place where the error between the true BFO and the BFO that my model predicted was smallest. And that came out here at the bottom, and that's like that point there. So that's how I did it. In a little bit, I'll tell you about how, so the ATSB, they did a similar thing, but they didn't enforce the fact that the BFO, the Doppler shifts were correct at each ping arc. What they did is they just did the following. They manufactured a lot of flight paths that had the right, crossed the ping arcs at the right time, and were they changed the circle from time to time. And then they looked at the errors between the actual BFO the model predicted and the BFO and the data. And this is my version of that. And so, and you see, this is really very strong evidence that shows that this uncertainty, this bias, that 5 hertz uncertainty plays a major role here, because you see that there's minus 5 hertz here, and here's 5 hertz, right? If the BFO data in the model and the BFO data, the actual BFO data matched exactly, all of these curves would go along this axis here at 0. But you see there's an error, and there's a 5 hertz error there, and there's a 15 hertz error there, and so on. So the red curve is pretty good because the error is like less than 5 hertz, okay? Right? And the green curve is also pretty good because its error is basically less than 5 hertz. So both of those errors are less than 5 hertz. And so the red curve and the green curve, wow, they fit the data equally well because there's that 5 hertz uncertainty in their data. And this distance is thousands of kilometers, right? And so that combination of that and the fact that we don't know where the plane started out, that's why this is a hard problem.
This actually makes sense, Dr. Zweck, because this is all guesswork from what I can understand and what I can tell, because you showed the yellow arc, the yellow line where they had their initial, and then they moved it 1,000 kilometers northeast. Then they brought it back again. So taking all these factors like your model, 325 knots, 400 knots, 450 knots, and according to you, the biggest problem is near that X mark after 90 minutes is just a guesswork where the aircraft was on the second arc, if I understand everything correctly here.
To some degree, yes. So when you have to make a guess and you're doing science, you want to ask yourself, how good is that guess? So you want to have some confidence. You want to build into your model some knowledge of how good that guess was. And so that means you have to build into your model all the errors that can occur. And this is the real problem with my approach, because I did it in an ad hoc way. All right. Because I was coming from applied math and from geometry, and I didn't understand how real aircraft work, and I didn't understand how real satellite communication systems work. But there is a piece of work that was done by a group of people, and I'm going to show you a little bit about, tell you a little bit about what they did. And so let me just sort of like, hold on, just go right up to the beginning of this. I got this, downloaded this PDF from somewhere a long time ago. And this is a group by the Defense Science and Technology. This is a book by the Defense Science and Technology Group in Australia. These authors are, as far as I can tell, they're very good statisticians and very strong training in the sorts of scenarios that we're dealing with this flight issue, because they're working with defense things. So they're working with, missiles and planes and all that stuff. So they are experts at this. And they used what's called a Bayesian method, which is a statistical method to try and understand what was going on. And I'm not going to describe all of what they did. I'm just going to say a couple of things. I'm going to show you a picture. So their approach. So the team in the ATSB took an approach that's similar to mine, and they got this green curve, right? They called this the error optimization approach. I used optimization in what I was doing too. It's like that least squares thing I was talking about. You want to fit the data with the smallest error. And they were saying they think the plane is roughly here. Well, I said it was a little bit further along, like maybe there, right? So I was out compared to them. And their model and my model were based on these great circle motions between one ping arc and the next. These people, they used what they call constrained autopilot dynamics. And that's the stuff in this book that I've just showed you using the statistical approach. And what they did is they said, we are going to make a very simple assumption, which is that the plane was set on autopilot and in such a way that its heading was constant. So the heading, the simple way to think about a heading is to say, okay, let's imagine the plane is traveling, from Perth to London, right? Going in the opposite direction. And so if you've got the North Pole up here, compass direction, and I'm going to go in a direction so that I'm always heading at, northeast, right? And so I'm going to make that assumption. So they use this constant heading model. And a constant heading model gives you a path on the surface of the Earth, which is not a great circle. It's a little bit different from it. So that's the biggest difference between their model and the data error optimization model. And then the other thing that they did was they said, okay, we're going to assume that that we sort of have this cruise dynamics, they call it, we're going to assume that its heading is constant, right? We don't know what its speed is. We don't know, sorry, I'm just, we don't know, we don't know what the wind effect had, right? Because the wind will, even if you have a constant heading, and there's wind, then the plane will move relative to the ground. So there was uncertainty there. So what they did is they said, we're going to build that uncertainty into our model. And then they also said, well, we could be that the plane is going to make slight turns, left or right, or it could accelerate, go a little bit faster or slower, or it could change vertically a little bit. So they sort of put into their model the ability to do that. And then they generated tens of thousands of flight trajectories. And they said, I'm going to make tens of thousands of these. And they all sort of come from this model, and they all have this randomness built in, and the randomness is pretty realistic. So I think this is a really good way to go. And then when they do that, you're creating what in Bayesian analysis is called a prior probability distribution. And then they take all of those guys and they say, well, which ones of them match the data? Which ones of those flight paths cross the ping arcs at the right time and have the right Doppler data, right? Or the right BFO. And so they put in the uncertainty due to that bias in the BFO as well. And they used very rigorous statistical analysis to do all of this. And then when they did that, they said, okay, when I do this, this fact that there's a big peak here. So this is the probability. It's saying it's like a histogram that you might have seen in a high school math class or statistics class. It's saying there's a very high chance that the plane was here, which means it was like, here's the arc. Very high chance that the plane was here because that's the peak of that histogram. And there's a very low chance that the plane was down here. And there's a fairly small chance that it was here, right? And you see here, they have all these trajectories that they're using to create these pictures. So this model has the advantage that it builds in a more realistic way that the plane could have gone on autopilot. It's taking that information into account, and it's taking all these uncertainties into account. So, so then, the data error optimization people, they moved the interest side up here and they searched in this area. And then this work took a long time to complete. It was very sophisticated. It took a few months to complete. And then later on, October the 8th, right? This is a week before my paper was published, right? They came out with their results. It was sort of phenomenal that they got it that quickly. Actually, it took them 5, 3, 10, about 6 months, right? Yeah, 6 months, 7 months to do that. That's phenomenally fast in science. And so they got this result. And so then they had to convince the other people that they were working with that was really serious, and they convinced them, and so they moved the search area back down here. So I actually think that I believe this one more because I think the model is better. Now, there are people, I know somebody who's a statistician that I respect very well, who had some disagreements with something about the approach that was taken here. I don't know what the disagreements were, right? But that's just natural in science. And I don't know how much that person that I know really knew about all the details. I don't know. But that person I have a high respect for. So the other, so let me just stop there with that question that you had.
Yeah, I want to ask you one thing. This is great stuff. So at what point, and I want to understand this, at what point did they stop moving the radius from one arc to another? So for what I mean to say is they moved 1,000 kilometers northeast, then they moved back. Here on October 8th, it says search area was shifted 800 kilometers southwest. So my question to you, what I want to ask you is, at what point were they satisfied that this does not have to be moved and this is where we think it is?
Okay, if you want to understand that, what you should do is read this 400-page document. So this 400-page document, I got it as a link, an archived link off of the Wikipedia page for MH370 in the references section. And so this is the official report written in October 2017. It's the last official report written by the ATSB. And I would just encourage your readership to read this through for yourself. This has got a lot of technical stuff in it, but it's actually not that hard to follow the general gist of it. And the shorts, so I read it yesterday. It's really fascinating. The search direction, the search position was changed according to the notes that I took yesterday in June 2014, late August, early September 2014, and December 2015. All right.
3 times.
So, but those are, but there were more smaller things along the way, right? So, yeah.
Great. So what we're going, I want to let our audience know that the Bayesian method, the PDF that Dr. Zweck sent us, it is in the description below, and we will also list this ATSB operation search for MH370 link or PDF in the description as well. And you said this is from the Wikipedia of the MH370.
I'll send it to you afterward.
Please, please, if you don't mind sending it to us, we will put it in the description. So okay, great stuff here. And you have answered few questions while you were talking early. You did talk about the physical constraints. You did talk about the flight maneuvers or turns. So you did that. So those questions have been answered. Let me see. Okay, I don't know if I asked you this. What are the primary mathematical limitations and sensitivities when you're trying to convert a noisy satellite timing and frequency data into a definitive trajectory?
Which of your questions is so I can read it on the page? I'm sorry, I'm getting tired now. We've been talking for a long time already.
No, it's okay. So this was, I think, question number 9.
Okay.
If we did not cover this,
I think I talked about that issue already.
Okay, that's fine.
The issue of the noise issues and going from that. I think I covered that. And my answer to that is that the best way to deal with that is with this Bayesian approach that the defense group did, that I just, they have that book about. Yeah.
Okay. So that's done. Number 10 about the models you did talk about in detail. Now we have a couple of questions left here. So let me see. Uh, 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 okay, this is a great question. So, as a mathematics educator, how do you effectively communicate mathematical uncertainty and probability to non-technical audiences, journalists, and especially to the families who are still seeking answers 12 years later?
Yeah. Well, I mean, that's been my goal today, pretty much. Um, I don't know if I've succeeded at all. I think you have to be very clear about what is known definitively, and what's not known definitively, and what's known about in the data, and what's known about the errors in that data. And you have to be very clear that in order to get an answer out, you have to use a mathematical model to work out how to connect those data points. And those mathematical models have assumptions. And so people have to, independent experts or independent people following this story have to sort of say, well, do I believe the assumptions that went into these models or not? And some of the modeling is highly technical, particularly this Bayesian stuff is highly technical. And so it's hard to read if you're not an expert. And so that's why I tried today to sort of simplify some of that stuff down a little bit to help people understand it, what the big pictures are. I would also say a couple of other things. It's an absolute, this was a great tragedy, but it's an absolute miracle that we know as much as we do about what happened. Right? It's if you didn't have that Inmarsat satellite data, that people would know nothing. And they might not have even known to look for this debris that came up in Reunion Island, right? So, and they would have been waiting. The debris churned up over a year later. And so that would have just been terrible. So we don't know everything about what happens, but we do know quite a lot. And I know that that's not nearly enough for the families and the friends of the people who were on that plane. But that's actually more information than you would think might be possible initially, right? And so that's really remarkable. And then, I think we have to keep our expectations in check. I don't think that we can know just from modeling exactly what happened. And if you read this report that's on the screen now, they'll talk about all sorts of other data, that satellite data and hydrophone data and all this other data that people searched for to try and find a trace of the plane. And there are very few traces. So, yeah, I didn't quite answer the question, but I hopefully I did.
No, absolutely. So I'm going to ask you, I know we went a little bit longer. I'm going to ask you one final question on the Malaysian authorities granting Ocean Infinity another extension for the new search, for which they will conduct from November onwards, since due to the weather or their fleet is not available till then. Based on all of the time you have spent, the presentation you have showed being involved over the last 12 years, a decade or more, how confident are you that this plane could be found, would be found, or would still be the aviation's greatest mystery of modern ages?
Well, that's a 0-1 question, right? Like, if they find it, then we've got it, right? Until we find it, we don't have it. So it's sort of an impossible question to answer. Let me answer it in this slightly different way. If you want to work out where to look, you need to look at all the different data and see what parts of the data reinforces each other. Okay. And so there are three things that I think are pointing in a similar direction. And this is just came out of my reading of that ATSB report that I had up a second ago. These constrained autopilot dynamics model is a very good model. And it predicts a place to look that is consistent with two other things that we know about. The first is that people sort of did this. So the idea is that the plane fell dramatically into the ocean. So by the way, there's a lot of evidence now that it fell very dramatically straight down, right? It didn't have a glide path entry. So it's not too far further on from that ping, probably, although who knows, right, really, but it's not a long way further on. And so there was stuff on the surface of the ocean that then drifted all the way to Africa and was detected at a certain time. And so they did modeling, mathematical modeling, knowing the information about the wind and the currents in the ocean to work out where that stuff could have come from. And that's also an inverse problem. It's an impossible problem to solve, right? So I don't know how much confidence I have in that modeling because I'm not an expert in that at all. And there could be some confirmation bias in that modeling too, right? In other words, people think that the plane went down here, and then they do modeling, and then they sort of see if it went down here, then if you do a simulation a certain way, you can see it'll end up in the Reunion Island, right? So there could be some confirmation bias there. But that drift modeling is consistent with this constrained autopilot dynamics result. And the other thing, which a couple of years after the plane went down, I think, or at least a year, there was a French satellite had taken data, and they did some analysis of that data, and they think that they could observe up to 100 pieces of debris in the water in an area that was also consistent with that drift. And it wasn't that far from the site of the crash, and it was about within a week or two that satellite image was taken, even though they only analyzed it much, much later. So that's not definitive either, but those three pieces of evidence together seem to support this area down here as opposed to this area up here. So, now the ocean is between 2 kilometers and 5 kilometers. The ocean floor is between 2 kilometers and 5 kilometers deep. And the technology that they have to look at the bottom of the ocean floor is extremely good, but it's not perfect. So, still a really, really hard problem.
Wow. Well, Dr. Zweck, this was actually quite a fascinating conversation, extremely informational. Thank you for educating us. And I want to ask our audience to please share this episode. And in a world of fleeting digital noise, our collective attention is the only thing that keeps the search for the truth alive. By listening, you ensure this story and the 239 souls it represents are never truly lost to the deep. Dr. John Zweck, thank you so much for taking the time, for walking us through this detailed presentation. And this has been such an honor for me. And personally, on behalf of also MH370 community, thank you so much for adding your valuable perspective to our series.
Thank you very much. I appreciate the opportunity.
Thank you. Take care. Bye-bye.
Right. Bye.